Now, whenever you're given a composite function, there are two ways to do it. You can go straight ahead and plow your way through. So if I want the Maclaurin series for this function, I know f of x is sine x squared f prime of x is equal to 2x cosine x squared. Okay, this is going to get pretty ugly pretty quick. The second derivative of x is minus 4x squared cosine x squared plus 2 cosine x squared. All right, now I enjoy doing derivatives, but this is going to get tedious really fast. So let me do a different method. You can do it straightforward. You can use the definition, but let me look at a function that I know, g of x. And g of x is equal to sine of x. And I know I can expand this as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Now let me just put my nth term out here. Negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1 factorial plus. All right? Now, I know that g of x squared is sine of x squared. So you remember the theorem we had? I can simply replace x squared in each of these x's. So sine of x squared becomes x squared minus x to the 6th over 6 factorial plus x to the 10th over 5 factorial minus x to the 14th divided by 7 factorial plus dot 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 negative 1 to the n. Then we put in x squared, so it's going to be x squared times 2n plus 1 divided by 2n plus 1 factorial. You can always do the straightforward method, but this may be tedious and it may take you a very, very long time. It's much easier when you recognize you have a composite function to write the formula for the general function and then do substitutions. You may need to add, subtract, multiply, divide. You may need to do a derivative. You may need to integrate. But this is much easier than this method.